Hello, I am Matt Wymore from the Department of Electrical and Computer Engineering at Iowa State University. I'd like to acknowledge my co-authors listed here. In this presentation, I will be talking about life cycle management protocols for batteryless intermittent sensor nodes. In this talk, I'll go through our motivation, talk about what is a lifecycle management protocol, talk about some specific LMPs that we are proposing for communication between batteryless intermittent sensor nodes, present evaluation of those protocols, and then conclude with a summary. For many, the grand vision of sensor networks is ubiquitous sensing. But if you power all these sensing nodes with batteries, you could be looking at needing to regularly change the batteries on thousands of nodes, right? Which is expensive and time consuming. What if you want to embed sensors in concrete or inside wind turbine blades? And even if you have rechargeable batteries and energy harvesting, you still have durability and lifetime concerns for those batteries. And then finally, manufacturing and disposing those batteries also presents an environmental concern. With that in mind, we are looking at an emerging class of computing systems called intermittent systems. So in intermittent systems, there is no large-scale energy storage, just a relatively small temporary energy buffer such as a capacitor. This capacitor is charged by small-scale energy harvesting, such as RF or vibrations. The end result is that nodes typically don't have enough incoming energy to operate continuously. And they instead operate intermittently, as shown here. All right, so this shows voltage on the system's energy capacitor over time. You can see there is an off threshold. The system can't function if the voltage is lower than that. And there's an on threshold. So what happens is the capacitor charges up to that on threshold, and then the system turns on. As it operates, it consumes the energy on the capacitor until eventually the voltage drops down to the off threshold. At this point, the entire system loses power and goes through a period of off time until the capacitor charges back up to the on threshold. So we call this cycle of on times and off times the life cycle of the system. Unlike traditional duty cycling, in the life cycle, the entire system is either powered or unpowered. So there's also a distinction between batteryless intermittent systems and traditional energy harvesting systems. Since intermittent systems neither store nor harvest large amounts of energy, we expect them to reach the off threshold. Right, so the goal in intermittent systems really is not to stop the system from turning off necessarily, but rather to deal with the off times gracefully. Now, every time there's an off time, the system loses all volatile state. So that includes RAM and CPU registers, which means any progress made on long computations that hasn't been saved to non-volatile memory is also lost. It also means that traditional clocks are not able to run during off times. This creates challenges for sensing, and in particular the scheduling of sensing, and also for communication. Right now, not only do the wireless radios of both nodes need to be on for communication, but the nodes themselves both need to be powered on at the same time in order to achieve communication. So the life cycling behavior of intermittent nodes makes it hard for applications to get things done. So that brings me to our proposed concept of life cycle management protocols, or LMPs. The idea here is that we will design protocols to manage the life cycle as best we can. We don't have much control over the life cycle, but we will make use of whatever control we do have to support the application. We'll do this using a methodical, protocol-based approach. Now, some key considerations when thinking about LMPs. First, the energy source that we're harvesting from is probably not controllable. It's external, it's variable, and it may be unpredictable. So owing partially to that fact, then the life cycle control mechanism that we have, meaning the levers that the LMP is going to pull, are imprecise. So next, then, off time is likely to dominate the life cycle, with off times of hundreds of seconds or possibly much longer. And on times are likely going to be in the range of hundreds of milliseconds. So, but as long as we are harvesting energy, right, the node is eventually going to turn on again. So at that point, we can't really store more energy, so that gives us something of a use it or lose it mentality. So when we do have an on time, we're not necessarily trying to conserve that energy, we're trying to use it to make forward progress with the application. All right, so what are some potential life cycle control mechanisms then? So this is our same picture of an intermittent system. Capacitor charges up to the on threshold, the system has on time, the voltage reaches the off threshold, then we have off time until the capacitor charges again. All right, so that's the life cycle. How can we manage this? One option is that we could have a dynamically variable capacitance for our energy store. Right, so for example, if we go with a smaller energy store, that will steepen our charging curve here and shorten our off times, right? But the trade-off is that will also make our on time shorter because we're storing less energy. Another possibility is to have a dynamic on threshold. Right? For example, if we adjust the threshold upward, as shown here, this would mean that more energy would be stored, and thus we would have a longer on time, right? But it would also mean a longer off time to charge up to that threshold. So whether or not that's whether that's good or bad would depend on the application, and the point of the LMP is to be able to make that decision to support the application in real time. Another potential lifecycle control mechanism was what we call early die capability. So our test platform has this capability. So this is the control mechanism that we use in the LMPs proposed in this paper. Now, early die capability simply means that a node is able to manually turn itself off early, meaning before it runs out of energy. So as an example, this node may decide right here, right, that it is done with its on time, and it will turn itself off. And of course, I don't mean a low power state, I mean completely unpowered off. This effectively skips part of the life cycle. The off time is started early, right? But since not as much energy was depleted during the on time, then this next off time isn't going to be as long, assuming that we have the same charging rate that we had before, which isn't necessarily true in an intermittent system. So again, this is imprecise control. All right, so this shows how a conceptual diagram of how the LMP fits into the software and hardware of an example system. So I really have time here to point out that we've drawn the LMP here outside of the other software modules, right? None of these things function without power, so they all depend on the LMP. Also, this reset line here represents the early die capability of the system, which is controlled by the LMP. So this signals the voltage regulator to turn off VDD to wait for the capacitor to charge back to the on threshold. So aside from the idea of LMPs, we are also proposing some sample LMPs that are focused on wireless communication between batteryless intermittent sensor nodes. The goal of these LMPs is to create communication opportunities, that is, overlapping on times for the two nodes. So during overlap, communication can occur using active radios and whatever network stack you want. The LMP is separate from the network stack. So the LMPs that we propose here fall into two categories. We have stateless protocols, which don't maintain any information across off times, and then we have stateful protocols, which do track some information across on times, specifically some clock information. Our first LMP is called null LMP. It is stateless and it functions as our baseline because it represents what happens if the node takes no action to manage its life cycle. Right, so in null LMP, nodes simply stay on as long as possible in every on time. So you can see that in this figure here, right? So note that our y-axis is now energy instead of voltage. But so here, each node simply stays on until its energy reaches the off threshold. So this actually maximizes the usable on time in a life cycle, but the probability of overlap here is small, particularly as the harvesting rate decreases and the off times become longer and longer. So what if we maximize the number of on times instead? So that's fast LMP. So this protocol is also stateless. In fast LMP, whenever a node turns on, it makes a single communication attempt, whatever that means according to the net stack. Right? If the attempt is successful, such as this one shown here, then the node remains on to communicate. Otherwise, it early dies immediately. It immediately turns itself off and begins recharging. So this results in a sort of sawtooth behavior that we call fast die cycling. Our third protocol is a stateful LMP called clock LMP. So the main idea here is that during communication, the two nodes will decide on a future rendezvous time when they'll both try to be on so they can communicate again. So here's the time of communication. Here is the rendezvous time that they've negotiated. So that rendezvous interval is basically a prediction of the node's remaining on time, right, plus the following off time, plus a safety margin. And then both nodes, right, calculate this, and we take the max, and that gives us the rendezvous time. So we can get the predictions of these amounts of time just using a simple moving average of past values. And once we've got this rendezvous set, whenever a node turns on, it checks how much time remains before the rendezvous. So figuring this out requires the ability to track time across off times. And we do that using a persistent clock. So more on that in a minute. But for now, if there's still a lot of time here, right, when we check the clock and there's still a lot of time until the rendezvous, then the node engages in the same fast die cycling that we used in fast LMP. Right? And because this fast die cycling creates a relatively short life cycle, the node is essentially able to sort of wait around for the rendezvous. And then when the node eventually turns on and finds that it's close to or a little bit past the rendezvous time, it stays on and tries to communicate for a full on time at that point. So ideally, the other node is also taking a full on time here, and we have overlap. Right? However, it's important to note that communication can happen outside of a full on time because the nodes are also attempting to communicate during the fast die cycling phase. So this means that if one or both nodes do not hit the rendezvous, right, which can happen for a variety of reasons, then the protocol still has a reasonable chance of successful communication here. Finally, what's not shown here, we do use fast LMP to bootstrap the protocol, get the initial communication, right? And we also fall back on fast LMP if we have too many missed rendezvous. So clock LMP relies on a continuous sense of time, meaning a sense of time that is unified across on times and off times in order to count down to the rendezvous. So since the onboard timers of the microcontroller won't function when the system isn't powered, we need an alternative to measure time across off times. One such alternative is a capacitance-based persistent clock, which works as follows. So first, during the on time, you use some of your system energy to charge up a small capacitor to some known voltage. Right? Then during off time, you allow that voltage to decay. So this figure shows experimental data for voltage discharge over time on a 1 microfarad capacitor and a 10 microfarad capacitor. So you can see here that if you measure the voltage at some point before the capacitor is totally discharged, then you can map that voltage to a time. Right, so the final step then is going to be when the system turns back on, measure the voltage on your clock capacitor, and then do that mapping. All right, one final protocol to mention, clock LMP Lite. So this is clock LMP with one modification. There is no communication during the fast die cycles. This means a few things. One, communication can only occur here, right, during overlapping full on times. And assumedly this is going to be close to the rendezvous. But the point of this is that the shorter on time during the fast die cycling will further shorten the off time. This will increase the frequency of the on times and make it more likely that the node has an on time that is at or near the rendezvous, right? Because it is possible that that actually won't happen in clock LMP. However, this reliance on communication at the rendezvous means that clock LMP light is considerably less robust to persistent clock error than the regular clock LMP. All right, that's all the LMPs we proposed in the paper. So we evaluated them with Python event-based simulations that simulate two intermittent nodes equipped with RF harvesting and a 50 millifarad energy store. In the simulations, we're looking for overlapping on times, aka the communication opportunities that are arranged by the LMPs. We require at least 8 milliseconds of overlap to count as a communication opportunity. We also account for a boot up time in which no communication can occur. Perhaps most interestingly, our simulations are driven by actual experimental life cycle data. So all of the on times and off times that we use in the simulation are derived from distributions of on times and off times that we obtained from the setup shown here. So this is a Texas Instruments sensor tag, which is powered by a PowerCast RF harvesting setup. So this picture shows the power transmitter, the harvester, the sensor tag here, and a lifecycle profiler, which is a separate microcontroller that logs the on times and off times of the sensor tag. So let's talk results. This shows the average overlap count, which is a count of the communication opportunities provided by the LMPs over the course of a 1-hour simulation. So we don't really have a state-of-the-art to compare to, so we normalize this number to our baseline, which is null LMP. So higher is better. The error bars here show the middle 90% of the data. In these simulations, both nodes are 1 meter away from the power transmitter. The x-axis shows the expected magnitude of relative clock error of the persistent clock. So from 0 to an average of 10% clock error. A few things to call out. One, with no persistent clock error, clock LMP and clock LMP light both perform over 10 times better than the baseline. So as expected, clock LMP light degrades quickly with clock error, right? But clock LMP is robust to the clock error. Fast LMP also performs pretty well for being a simple stateless protocol, and it is unaffected by clock error since it doesn't use the persistent clock. And finally, note that this x-axis goes to 10% clock error. So the question you might ask is, how realistic is that? Well, here is some clock error experimentally obtained from a state-of-the-art persistent clock prototype. So as an example, the error here at 100-second off time is about 1 to 2 seconds, which is significantly less than 10%. Of course, some of the other off times have higher error. So on the next slide, then, we also evaluate using this experimental data. This is results for median and 95th percentile intercommunication delay for different harvesting distances. So we define intercommunication delay on the y-axis as the time between consecutive overlaps. So lower is better. The x-axis shows the distance of one of the nodes from the power transmitter. The other node is fixed at 1 meter. So on the right, to put it in some context here, we're showing the distribution of off times that correspond to those distances. You can see the off times range from a few seconds at half a meter to hundreds of seconds at 3 meters. So going back to the bar chart then, a few spots to look at half a meter, clock LMP performs well with both 1% simulated error and using the experimental persistent clock data. That's what the with PC means here. Fast LMP also performs pretty well, but its performance degrades more quickly as the harvesting distance increases. Right, and so finally, the most important point here, just remember that our null LMP in a way represents a lack of a protocol. And so in that light, right, across the board, using any sort of LMP has a significant performance benefit, demonstrating the usefulness of the LMP concept as a whole. So more results can be found in the paper, but in summary, intermittent systems are promising, but there are some difficult challenges presented by the intermittent life cycle. So we're proposing a protocol-based approach to manage this life cycle in support of the application. We propose communication-focused LMPs, and our evaluations showed these protocols providing up to a 10x improvement over the baseline in the number of communication opportunities experienced by a pair of batteryless intermittent sensor nodes. So that concludes this talk. Thank you for your attention.